Okay, so in this video we'll go over the DES decryption process and how the Feastel network is used for decryption. Okay, so we have the 64-bit ciphertext that is input to the decryption process. So it goes through this permutation, which is the same table that we used before for the final permutation is being used. Okay, and then we split that order comes out of the P box into two sub halves, the L16 and R16. And so L16 and R16 are fed as input to cycle 16. So this is actually the first cycle for decryption. So we feed in the 64-bit key that is processed similar to how it was processed for cycle 16 for encryption. So same way the key is processed for the cycle. So for encryption we know that L16 was R15. So for decryption L16 is fed back as R15 now. So that's the kind of symmetry we have between encryption and decryption, because we know for encryption R15 is same as L16. So when you do decryption we are going to just pass it back like this. So L16 is going to be R15. So R15 is fed to the cycle 16, and we feed in also the 64-bit key, and we feed in R16 to the cycle. So R15 and R16 basically get inside, and with this key you get back this L15. So now we have this L15 and R15 which are now fed to cycle 15, and the same thing repeats. So eventually, so for example, you have L2 and R2 fed to cycle 2 with the cycle key, the key for cycle 2. What you get out is L1 and R1, and both are fed to cycle 1. So L1 is essentially now R0, enter cycle 1 along with R1, and 64-bit key you get L0. So now the L0 and R0 are put together, goes through the initial permutation, and what you get out is the 64-bit plaintext block. Okay. So if you want more details about the decryption process, again, so we have this for any cycle I, we have this Li and Ri fed to the cycle. So Li is now same as Ri minus 1. So Ri minus 1 enters the cycle along with the Ri. So the Ri minus 1 goes through this Feastel network process, and the key for that cycle is also fed in as 48 bits. So whatever happens here is the same thing that happens also for encryption. So there's no change. So what we get out of the Feastel network is a 32-bit quantity that is XORed with the Ri coming from here. And so that's what is this. So Ri XORed with whatever comes out of the Feastel network by passing Ri minus 1, which is same as Li and this Ki, and what you get is Li minus 1, and this continues for all the cycles. Now we saw the SBoxes during encryption, so let me explain again how the SBox is used. So it is used in this case you get a 48-bit output after you do the XOR with the expanded right half and the key, and that 48-bit output goes through the SBox process, which is combination of both substitution as well as a permuted choice. So what happens in the SBox is this. So you have this 48-bit input broken down to 6-bit units. So each 6-bit unit is fed to each of the SBoxes. So the first 6-bit unit is, like in this example, it is 0, 1, 1, 0, 1. So these 6 bits are fed to the first SBox. So the first and the last bit are like 0 and 1, and which in decimal is 1. The middle bits 1, 1, 1, 0 together, the decimal value is 14. So basically we index into SBox 1 using the row index of 1 and the column index of 14. So the row index of 1, so this is xbox 1, row index 1 and column index 14, you get 3. So 3 is the output, and we write that in binary. It is going to be 0011. Okay. Now for SBox 2, we take a bit 7 to 12, and that is 010010. So we can now use the leftmost and rightmost bits, 0 and 0. In decimal it is 0, and then we have 1001, that is going to be in decimal 9. So in SBox 2, we index using row index 0 and column index 9. So SBox 2, row index 0 and column index 9, it turns out to be 7. So we can write that in binary 000111, that is 7. So essentially each 6-bit unit is kind of permuted choice reduced to 4-bit output. So 8 such SBoxes, so it's 8 times 4 is 32-bit output. So that's how SBoxes are used. Now one property of SBox is if even one of the 6 bits that are passed in SBox changes, at least 2 of the output bits will be different. So that's what we're going to illustrate. So let's take the same 6-bit input that we used in the previous example, and if we go to the regular processing like we just saw it, we get these 4-bit outputs. So I'm going to change the last bit of each of the 6-bit inputs. I'm going to just change them from either 1 to 0, 0 to 1. So this was like 0, 1, 1, 1, 0, 1. So I'm going to change that as 0, 1, 1, 1, 0, 0. Just changing the 1 to 0 and changing this 0 to 1 and then 1 to 0, 1 to 0 and so on. So now we repeat the same process of looking into the SBox. So now this is like 0 and 0 put together is 0, 0, which in decimal is 0. Then the middle bits are 1, 1, 1, 0, which is 14. So now we index with the SBox for row index 0 and column index 14, which will get as row index 0 and column index 14 will be 0. So what comes out of the SBox here is 0, so which in decimal is 4 zeros for 4-bit. Similarly, I changed this 0 to a 1. So if you now use the left and right most bits, it will be 0, 1, which in decimal it is 1, and 1, 0, 0, 1 is 9. So if indexed into SBox 2 with row index 1 and column index 9, it will be row index 1 here and column index 9. It is also 0. So we have 0 in decimal is going to be 4 zeros in binary. So we repeat this process. So essentially now you can see here this 2 zeros, here it is 0, 0, 1, 1. Similarly here we have 2 zeros, whereas here it is 1, 1. So at least 2 of the, actually here in this case 3 output bits changed, right? So but basically at least 2 of the 4 output bits will be different if you change the just 1 bit in the 6-bit input. So that's the property of SBoxes. So SBoxes have been designed in such a way they are not that easy to be able to can predict the values of the outputs. So it's very difficult to predict the value of the outputs. Okay, so it's not either a linear function or even a little bit more complicated function. It's called the affine function. So it's very difficult to predict what are going to be the 4 output bits for the 6 input bits. Okay. Now some of the weaknesses of DES. So if you have say some plain text and a key for which you get a ciphertext for any plain text and key. So basically if you take the ones complement of the plain text and the ones complement of the key, again by ones complement is just like all zeros are changed to 1 and all ones are changed to zeros, we get the complement of the ciphertext. So someone can misuse this for cryptanalysis. Now there's also another weakness which is to do with this weak keys, which means if all the bits in a key are either zeros or ones, so irrespective of the shift that we do, because we do some left shift by 1-bit positions or 2-bit position depending on the cycle, but if all the bits in the key are either zeros or ones, it's not going to change, which means it's the same key that is passed to every round of DES. And that way it is very relatively more easy to predict what is going to be the ciphertext. Okay, and the same problem happens if the first half of the 64 bits, like the first 32 bits are zeros and the next 32 bits are ones. Same way, if the first 32 bits are ones or the next 32 bits are zeros, the same problem is there. Now, semi-weak keys, this is something that will be easily usable for cryptanalysis. So, for certain key pairs, because I think I said earlier, if you, for a given plain text, if you change the key, the ciphertext should be different. Because that's what makes it difficult for cryptanalysts to find out what is the right key that's being used. But for certain key pairs, K1 and K2, if I encrypt, say, the plain text with K1 and get some ciphertext C, I get the same ciphertext if I encrypt that plain text P with K2. So such pairs of keys, K1 and K2, are said to be what is called semi-weak keys. So DES does encourage, or does not encourage, but does allow or permit use of such keys like this. So the way DES is structured, it cannot handle semi-weak keys. Okay, so there could be like two keys, K1 and K2, for which you use either one of them, you get the same ciphertext for a particular plain text, which is not a good property. So to improve DES, even though again it is a 64-bit key, but we remove every 8th bit, so what we get is a 56-bit key. So with 56 bits, it's more easy to do even a brute force attack, because all we need to try is try 2 to the 56 possible keys, and it's quite easy to do in a very fast fashion without spending more time. So some improvements to DES, or like this proposals for a double DES or triple DES. So in double DES, we basically use 128-bit key and use the first 64-bit as the key K1 and the second 64-bit as the key K2. So what we do is essentially like go through 2 levels of DES encryption. So take the plain text and encrypt that with DES, go through the 16 rounds with key K1, and whatever you get as ciphertext, subject that to another like 16 rounds of DES encryption with key K2, and whatever you get finally is a ciphertext. So in order to decrypt, we have to go through 2 levels of decryption. DES decryption, first the ciphertext and the key K2. What you get out of it, you have to pass it to DES decryption with K1, and you get the plain text. Now, triple DES is a little bit more complicated in the sense that we use 168 bits as a key, but the idea is still the same. The first 64 bit is K1, the second 64 bit is K2, and the third 64 bit is K3. So again, we could interchange doing the encryption and decryption because it's the same physical network. So we can proceed from backwards, and that could be also called as an encryption. But we know that's called decryption. As I say here, we say K1 encrypted, the plaintext encrypted K1, and then when you do the encryption K2, you don't go from top to bottom. So you don't go from round 1, 2, 3 up to 16. You go from the bottom to top. So that's why I say this D of K2, and whatever comes out of this encryption. So you go from round 16 and 15, 14, and so on. And then whatever comes of that encryption, you again go through a top to bottom around 1, 2, 3 encryption for DES with key K3. So when we do like this, follow this order for encryption, we have to do relatively this related order for decryption. So this ciphertext that we get it by encrypting with K3. So we have to decrypt the ciphertext with K3 first, and whatever we get out of this, we have to do a kind of encryption with K2, going from 1 to round 1 to so on up to 16, and then whatever we get out of this, we have to do a decryption with key K1. So that is like going from the bottom to top, round 16, 15, and so on. And triple DES has been found to be quite useful before the and robust before the proposal for AES came through. and it is used in several internet applications like the email security applications or email protocols like PGP and SMIME to provide email security. And also we don't need to have the same we don't need to have all the 168 bits to be different, or like the K1, K2, K3 could be related to each other. So we could have something like K1 equals K3 and K2, so that is okay. Now the last thing about DES is with the double DES, it is vulnerable to a kind of attack called the meet in the middle attack. So what it means is, like, this is how first of all the double DES is used. So you have the plain text encrypted with K1, and whatever comes out of it is encrypted with K2 further to get the ciphertext. So the kind of attack that is possible here is called the known plain text attack. So what a known plain text attack means, we are given with a plain text ciphertext pair, and we know that the encryption algorithm used is double DES. So what we are interested is to find the keys, and we know that in the case of double DES, each of this K1 and K2 are like 64 bits. So what we can do is, so to get so this is ciphertext. So to decrypt, what we have to do is we have to do the decryption with K2, right? So whatever we do the decryption with K2, what we get is this. What we get, the decryption with K2 of the overall ciphertext is going to give us what we got out of encrypting the plain text P with K1, because this is what you're encrypting further and getting the ciphertext, right? So if you're decrypting the ciphertext to K2, what we get is what we use to encrypt. So that what we use to encrypt is what came out of encrypting the plain text P with K1. So what we'll do is we'll try 2 to the 64 combinations of key values for K1, another 264 combinations of values for K2, and we can basically find for which combinations of K1 and K2 we get these two things to be the same. And actually we don't need to try the 2 to the 64 or 2 to 64, because double DES uses DES for this encryption decryption. So we know that in DES the 64 bits is reduced to actually 56 bits. So all we need to do is try 56 bits for keys for all possible 56 bit keys for K1 and all possible 56 bit keys for K2. So which means we have to try just 2 to the 56 combinations of key values for K1 and another 2 to the 56 combinations of key values for K2. And on average, as I said before, when you do the exhaustive search, you don't have to try all the possible combinations. By the time you have searched half of the combinations, you would on average be successful. So essentially you don't have to try 2 to the 56 combinations of K1, just half of it is like 2 to the 55. Same thing, half of K2 is 2 to the 55. So basically you try 2 to the 55 combinations of K1 plus another 255 to the 55 combinations of K2. That will be like 2 to the 55 plus 2 to the 55 is 2 to the 56. Okay, so which means you might be thinking the double DES is using 128-bit key, even if and broken down into 264-bit keys K1 and K2, and which means you need to try like 56 and another 56 112 bits. So you have a 112-bit K1 and K2. That's what it looks like at the outset. But you don't have to try all possible combinations of 2 to the 112 bits, because this K1 and K2 are not used together. Okay, so they are split and they are used as a 56-bit K1 and a 56-bit K2. So since they are used separately, all we can try is 2 to the 56 combinations of zeros and ones for K1 and another 256 combinations, 2 to the 56 combinations of ones and zeros for K2. Again, it will be sufficient to try half of them. So 2 to the 55 plus 2 to the 55, that would make it, so 2 to the 55 plus another 2 to the 55 for K1 and K2 together. So that is like 2 times 2 to the 55, so that is 2 to the 56. So it's not like K1 and K2 are together and it is 112 bits. If it was like that, we would have needed 2 to the 112 combinations of zeros and ones in the worst case, or 2 to the 111, but we don't need to try that many combinations. Okay, so that is this vulnerability with the meet in the middle attack. So that will stop here.